Hello everyone, welcome to the 10th video of our lecture series. So in this lecture video, I will talk about addition of angular momentum. So I am not going to solve any problem today. So I am going to tell you about the theory of addition of angular momentum. So this is extremely important. So addition of angular momentum. So this addition of angular momentum this encountered in almost all areas of modern physics. So, for example, suppose we have an hydrogen atom. So in hydrogen atom we have electron. So there will be total angular momentum of electron, which will consist of its orbital angular momentum and spin angular momentum. So orbital angular momentum, this is due to its orbiting motion around proton, and the spin angular momentum is due to its intrinsic spin. So until we don't know how to do this addition of angular momentum, we cannot describe or discuss properties of hydrogen atom. So that is why it is extremely necessary to know the concept of how to add different angular momentum. So let us proceed with that. So suppose we have two angular momentum, J1 and J2. So they are two different generalized angular momentum. They can be orbital angular momentum or spin angular momentum. And they belong to different subspace. That means they can be of different particles. Suppose you have two electrons, so this angular momentum can be of two different electrons. That means can be of different particles. Or it can refers to different properties of same particle. So for example, spin angular momentum and orbital angular momentum of electron, that's what we are talking about. So we have these two generalized angular momentum. Now we know that the components of J1 and J2, they satisfy the commutation relation this. So this is for first subspace that we are talking about. And similarly for second subspace we have this relation. And so on, like the previous. So just replace 1 by 2. So these are the commutation relation of different components of J1 and J2. So and as J1 J2 belong to different subspace, so their components also must commute. That means we can write as J1 J J2K. It will be 0. So J and K can be any of the X, Y, Z. That means the components of angular momentum of two different subspace, they must commute. So this is basic. So now we know that J1 square and J1J, they have eigenstate J1 M1. So since the J1 square and J1J, we can simultaneously diagonalize them. So they have same basis and it can be represented as J1 M1. So where we know M1 can run from minus J to J. And similarly, J2 square and J2Z, they have eigenstate as J2 M2. So these are 1. So where M2 can have values from minus J2 to J2. So formally we can write JK square JK MK, it is equal to JK into JK plus 1 H cut square JK MK, and we can write JKZ JK MK, this is equal to MK H bar JK MK, where K can be 1 or 2. So K1 is for first subspace and K2 is for second subspace. So now J1 that belongs to space of dimension 2J1 plus 1, because M1 can have values in this range. So there are 2J plus 1 M1 values. So that is why J1 has space of dimension 2J plus 1. Similarly, J2 has space of dimension 2J plus 2J2 plus 1. So it will have 2J2 plus 1. So now if we consider these two subspaces 1 and 2 together, then J1 square, J2 square, J1Z and J2Z, they will form a complete set of commutating operators. So if we consider J1 and J2, that means, so if we consider 1 and 2 subspace, together, then we can say that J1 square, J2 square, J1Z and J2Z, they will form a complete set of commutating operators, because J1 square and J1Z commute, J2 square, J2Z commute, and also any component of two different subspace, they also commute. So this commutes with this and this commutes with this. Similarly, this one commutes with this and this one already commutes with this. So all these four are mutually commutating with each other. So that is why they form a basis and we can form a complete set of commutating operators. So all these four operators, they can be simultaneously diagonalized by same states because all of them commute. So they can be simultaneously diagonalized by same state, which will be eigenstate of all these four operators. So if we denote this state, which is eigenstate of all these four operators, we can denote this by J1, J2, M1 and M2. So, and what is the eigenvalue for these components? So this will be J1 square, J1, J2, M1, M2. So it will give us value J1 into J1 plus 1, H cut square, J1, J2, M1, M2. And for J2 square, so it will be the same state, and it is J2 plus 1, H cut square, we have our same state, and J1Z. On if we add J1Z on this state, we will get M1 H cut, same state, and J2Z. If we operate on this state, we will get M2 H bar, and we have this state. So that means this state is eigenstate of all these four operators with corresponding eigenvalues. Now we can show that this J1, J2, M1 and M2, this eigenstate span the space which is of dimension n, 2J1 plus 1 into 2J2 plus 1. So for this we have to show its orthonormality and complete relation. So we have to show that this is complete and this is also orthonormal. So let us proceed. So we know that this J1, J2 and M1, M2, this can be written as J1, M1 and J2, M2. So how can we write this as direct product? We can write this because this subspace 1 and subspace 2, they are independent. So that is why we can write this J1, J2, M1, M2 as a direct product of J1, M1 and J2, M2. So first of all, we have to show its completeness relation. So to do this, we have to do the following. So completeness means we have to summation over both M1, M2 values and J1, J2, M1, M2. If we multiply this with this state J1, J2, M1, M2, this has to be 1. So this is our completeness relation. And for orthonormal, we have to show that J1, J2, M1, M2, if we multiply this with another state J1 dashed, J2 dashed, M1 dashed, M2 dashed, so this product will give us 0, or we can write this formally as J1 dashed, J1 delta, J2 dashed, J2 delta, M1 dashed, M2, M1, and we have delta M2 dashed, M2. So that means if all the quantum numbers are not same, then it will be 0, and if all the quantum numbers are same, if at least is different from this delta function, we can say that it will be 0. So this is our orthonormal condition. So we have to show these two. So let us proceed with the first one. So we can write this as M1 summation over of M1, M2. I am write this in short form. So J1, J2, M1, M2, and we have J1, J2, M1 dash, M1, M2. So this we can write this as M1. This term we can write as J1, M1, J2, M2 from here, and we can write this term as J1, M1, J2, M2. So since these are independent, we can write this as M1. Here we have J1, M1, J1, M1, and this term J2, M2 multiplied with J2, M2 get. So now we know that this JM, they are complete. So this is also complete. This satisfies completeness relation, and this is also complete. So that means M, JM product with JM, this should be 1. So this term will give us 1, and this second term will also give us 1. So that means we have 1. So we can see that this eigenstate J1, J2, M1, M2, these are complete. Now similarly we can show the orthonormal relation. So let us proceed. So we can write J1 dashed, J2 dashed, M1 dashed, M2 dashed with J1, J2 and M1, M2. So we can write J1 dashed, M1 dashed, J2 dashed, M2 dashed, and this term we can write as J1, M1. So this is our first term, and second term is our J1, M1, J2, M2. So now they are independent. We can write this as J1 dashed, M1 dashed, J1, M1 and J2 dashed, M2 dashed, J2, M2. Now this we know, this is delta J1 dashed, J1 and delta M1 dashed, M1. Similarly, we know this is of the form delta J2 dashed, J2 and delta M2 dashed, M2. So this is from our single angular momentum, not this is our single particle angular momentum states, and we already know that they satisfy these properties. So we can see that this also satisfy the orthonormality condition. So since this J1, J2, M1, M2, these eigenstates, they are complete and they are orthonormal, so they span the whole space which is made up of subspaces 1 and 2. So we can say J1, J2, M1, M2, it spans the space, total space, which is made up subspaces 1 and 2. So formally we can write, if n is the dimension of the space, total space, then n is 2j1 plus 1 into 2j2 plus 1. Now we can write this raising and lowering operator in subspaces 1 and 2. So in subspace 1 we have our raising and lowering operator as j1x plus minus I j1y, and in subspace 2 we have our raising and lowering operator as j2x plus minus I j2y. So what will and it will satisfy this relation. So if we apply this j1 plus minus on j1, j2, m1, m2, what are the value we will get? We know that j1 and j2 are independent, so this term will only act on the j1, m1 subspace, and it will have the value h cut root under j1 minus plus m1 and j1 plus minus m1 plus 1, and it, since it only act on the j1 subspace, so it will only change the value of m1. It will not affect the value of m2. So we will have the state j1 j2, and here we will have m1 plus minus 1, and we have m2 as same. So similarly, when j2 plus minus, when this act on j1 j2 and m1 m2, so it will only change the value of m2. It will not affect the value of m1. So we will have again h cut. Here we will have j2 minus plus m2, and here j2 plus minus m2 plus 1, and this state will be now j1 j2's m1 will be same, and m2 will be changed by plus minus 1. Now this algebras are for subspace 1 and 2, so we have to now add this to angular momentum. So let us write this as j as j1 plus j2. So one thing you have to note that this is not a typical matrix addition symbol, because this j1 and j2, their dimensions are not same. So we can only add two matrices when they are of same dimension. But this j1 has dimension 2j1 plus 1, and this j2, it has dimension 2j2 plus 1. Now since j1 and j2 can have different values, so it is not necessary that this j1 and j2 should be same. So this is not a typical matrix addition. So this is just a symbolic addition. So now our main target is to add this to angular momentum, and we have to find the eigenvalues of eigenvector of j square and jz. So we have to find the eigenvalues and eigenvectors of j square and jz. So this belongs to the total space. So we have to find them in terms of what? We know j1 and j2, so we have to find them in terms of j1 square, j2 square, and j1z and j2z, because we know that in a domain of angular momentum, only one component of angular momentum and the square of the angular momentum, they can be simultaneously diagonalized. So that is why we have to find j square and jz again in terms of this. So there is nothing special about jz, since earlier we have assumed that j square and jz can be simultaneously diagonalized. So that is why again we are finding the eigenvalues of eigenvector of j square and jz in terms of this in terms of the eigenvalue and eigenvectors of these operators. So let us let us find the commutating properties of this j square and jz. So we know that j square, it can be written as j1 plus j2 squared. So we can write this as j1 squared plus j2 squared, and we have 2 into j1 dot j2. So j1 dot j2 we can write as j1x j2x plus j1y j2y and J1Z, J2Z. Now, if you solve this commutation relation J square, J1 square, we can see that it will be 0. So you have to just do the algebra. We write J square in as this, and J1 square you can write as J1x square plus J1y square and J1z square, and then do the commutation relation. You will easily find thus it will be 0. Similarly, J square, J2 square, it will also give us 0, and we have J square, JZ, this will be 0. But if you do the commutation relation between J square and J1Z, you will have this to be non-zero. And similarly, if we evaluate the commutation relation between J square and J2Z, we will have this again to be non-zero. So that means we can only simultaneously diagonalize this J square, JZ, and J1 square and J2 square. So only these 4 can be simultaneously diagonalized. We cannot diagonalize this J square, JZ, J1 square, J2 square, and J1Z and J2Z simultaneously, because this J square and J1Z don't commute, and J square and J2Z they don't commute. So that is why they cannot be simultaneously diagonalized. So only these 4 can be simultaneously diagonalized. So we have to find a relation between the state, between a state which will be denoted by these 4 quantum numbers, and we have a state which is denoted by these 4 quantum numbers. So we have to find a relation between them to find the eigenvalues of eigenvectors of this J square and JZ in terms of this J1 square, J2 square, and J1Z and J2Z. So let us denote the state which can be simultaneously diagonalized by these 4 operators. So let us denote that by J1, so we can denote this by J, M, and we have J1Z and J2Z. So this is our state, which can be diagonalized simultaneously by these 4 eigenvectors. So you have to find a relation between this and J1, M1, J2, M2. So all we have to do, we have to find a relation between this state and this state. So first formally we have to check that if this state they span the whole space or not. So we have to check this. So let us first write the eigenvalues of these operators. So if this J square act 1 Jm, J1, J2, so what we will get? We will get J into J plus 1 H cut square, and we have the state J1, J2. Similarly, what will be the eigenvalue for JZ? So for JZ, we will have M H cut, and here we have J, M, J1, J2. Similarly, what will for the J1 square and J2 square, we can write Jm, J1, J2. This will have the eigenvalue J1 into J1 plus A1 H cut square, and here we have Jm, J1, J2. Similarly, for J2 square, we will have this. So these are the eigenvalues for these four operators when they act on this vector. So here we can say that for each j, what will be the values of m? Similarly, we have 2j plus 1 m values, and what are they? They are from minus j to plus j. So j minus 1 and j. So here j1 and j2 are fixed. So we can write this j1, j2, jm. Since these are fixed, we can write this as jm. So this is in short form notation. So and now this jm, it's this span the total space. So as this span the total space, so that means they are complete and orthonormal. So what will be its complete condition? Complete condition is, so whatever we have first summation over m that runs from minus j to j, and then we have summation over j, because only we have j1 and j2 to be fixed. So this jm can have any values. So for each j we will have this 2j plus 1 m1 values. So, and for completeness we will have this j1, j2, jm, j1, j2, jm. So this should be 1. This is our completeness relation, and for orthonormality we will have this. So since j1, j2, jm and j1, j2, j prime, m prime. So what will be its value? Its value will be delta j, j prime, and delta m, m prime. So this total space is also known as product space, because it is a direct product of subspace 1 and subspace 2. So what we have to do now? So now we have to find a transformation that connects this jm with j1 m1 and j2 m2. So we have to find the transformation. Transformation that connects these two. So formally we can write that this jm, so we can write this as 1 product with jm, and 1 using completeness relation we can write this as m2, which will be from minus j2 to j2, and we will have m1, we will run from minus j1 to j1, and this j1 and j2 are fixed, and here we will have j1, j2, m1, m2 product with j1, j2, m1, m2, and we have jm. So in place of 1, using the completeness relation of this j1, j2, m1, m2 state, we can write this. So if we consider this, so this is the coefficient which we have to find. So these are known as Clebsch-Gordon coefficient. So this is Clebsch-Gordon coefficient. So by convention this coefficient is taken to be real. So if we write this as for now, consider this, if this is alpha, so we can write this as the summation term, and we will have this alpha. So j1, j2, m1, m2. So this alpha will depend on what values? It will depend on this m1, m2 values. So let us just write is m1, m2. So we have summation over m2 and summation over m1. So this is our transformation that will connect this Jm state with this J1, J2, M1, M2 state through which the Clebsch-Gordan coefficient which we have to find. So these are taken to be real by convention. So that is it for today's video. So in the next video we will discuss how to find this Clebsch-Gordan coefficient and how to connect this two states which span the same space. I mean which span the same product space.